Hi everyone, I'm Professor Wasim Jabi, and in this tutorial I'm going to be explaining the core components of topologic and how to create them. I will be using topologicpy inside of Jupyter Notebook. So before we start, let me show you the types of entities that topologic can create. As you can see here on the screen, we start with the simplest entity on the lower right corner, which is a vertex. A vertex is nothing more than a single point in 3D space, and it has x, y, z coordinates. When you take two of these vertices and you connect them, you get a straight edge. So that is the next entity in topologic, and you can create edges in different ways by start vertex, end vertex, and other ways. Now, if you take these edges and you connect them either head to tail or in any kind of network, you get what is called a wire. So a wire is equivalent, perhaps if you are familiar with Autodesk, the wire is equivalent to a polyline. Now, if you take these wires and you close them in a circuit, you can now get a face, and the face has area and has a front and a back. Now, if you take these faces and you can connect them by edges, you get what is called a shell. Think of a shell as a cardboard box that's open, or origami. It's basically made out of facets, or if you are familiar with other 3D modeling software, it's equivalent to an open mesh. Now, if you take a shell and you close it so that it can perhaps hold water, it creates a volume, that is, you get what is called a cell. A cube, a prism of some sort, is a typical example of a cell. And then if you take these cells and you aggregate them, you connect them so that they share faces. Think about soap bubbles, for example, a series of volumes that are interconnected by faces, you get what is called a cell complex. And then we have one last class or type of entity called a cluster, in which you can mix and match all of these other entities into one object. So you can mix a vertex with an edge, with a cell, put them together, and create what is called a cluster. Now, as a parent to all of these classes, we have a superclass called topology, and topology acts on all of these classes and can do other things, as you will see in later tutorials. Okay, so let's get started with the simplest type of entity, which is a vertex. So we're gonna switch over to Jupyter Notebook. And in order to create topologicpy entities, you have to import it. So I assume you have already gone through the process of downloading or pip installing topologicpy and having Jupyter Notebook, and your environment is ready to go. So how do we bring in those classes? The typical pattern is that you say from topologicpy, like this, dot vertex, which is the name of the class or the module actually, import vertex. Okay, so from topologicpy dot vertex import vertex. We do the same pattern for the rest of the classes, so we might as well take our time now and import everything that we need later on in this tutorial. So just bear with me. So from topologicpy dot edge import edge, from topologicpy dot wire import wire, from topologicpy dot face import face, from topologicpy dot shell import shell, and from topologicpy dot cell import cell, from topologicpy dot cell complex import cell complex. And please be careful about cell complex in terms of the capitalization. The two C's are uppercase and everything else is lowercase. And from topologicpy dot cluster import cluster. And lastly, from topologicpy dot topology import topology. All right, so now to run this, to run the cell, you can either press the run button on top of the screen, or as a shortcut, you can hold down the shift button and press enter. So that's what I'm gonna do right now. Shift enter. You'll notice now it has run and it's ready to go for the next step. So let's go ahead and create vertices. So the simplest way to create a vertex is to say vertex dot by coordinates. So the word by means that you are going to use the input in order to create a vertex. So edge by and start vertex end vertex creates an edge by kind of a list of input vertices. There are also some simple shortcuts. For example, if you want to create a vertex at 0, 0, 0, rather than say vertex dot by coordinates 0, 0, 0, you can just simply say vertex dot origin. So I'm going to create a set of 4 vertices that represents the corners of a square that is anchored at 0, 0, 0. And I'm going to call them V1 through V4. So V1 is equal to vertex dot origin. So I'm going to put that at the origin, which is 0, 0, 0. And then V2 is equal to vertex by coordinates 1, 0, 0. And then V3 is equal to vertex by coordinates 1, 1, 0. So I'm going anti-clockwise. And V4 is equal to vertex by coordinates 0 in the x, y in the y, 1 in the y, excuse me, and 0 in the z. All right, so now how do we visualize these things? How do we displace them? We have a simple method in topologicpy. It's called topology.show, and you basically give it the list of topologies that you would like to display. And also it has some options, for example, for vertex size or edge width, and you can give it edge colors and face opacities. But we're going to do a very simple version of it right now. We're going to say topology.show v1, v2, v3, v4. And in order for us to see it clearly on the screen, I'm going to specify vertex size. Again, be careful about the capitalization. The V is lowercase, but the S is uppercase. Vertex size is equal to 4 so that we can see it. Now we're ready to hit Shift Enter again in order to see the result. And here we are. We have now a 3D view of these 4 vertices that you can rotate and zoom in and out in order to see the result. Great. So moving on to the next class, which is edge. Let's go ahead and create the 4 edges that form that square by connecting V0 to V1, V1 to V2, V2 to V3, and then V4 back to V0. Okay, so here are the 4 vertices. You get a 3D view that you can rotate and zoom in and out. Great. So now for the next entity, which is an edge. So we are going to actually create the 4 edges that form that square by connecting the 4 vertices to each other. So we're going to go from V1 to V2, from V2 to V3, from V3 to V4, and then from V4 back to V1. So I'm going to call these edges E1 through E4. So here's how we do it. We start typing E1 is equal to edge by vertices. Again, be careful about the capitalization. And that takes a list of vertices. So as you know, in Python, a list of anything is represented by square brackets. So we're going to do square bracket V1 to V2. And we're going to create these 4 edges. We can copy and paste this line and just change the name of the variables. So I'm going to go ahead and Control-C to copy this and paste it 3 more times for the 4 edges. And I'm going to rename the variables. So the next one is E2, and the next one goes from V2 to V3. And edge 3 is going to be called E3, and it's going to go from V3 to V4. And the last one, edge 4, is going to be going from V4 back to V1, back to the first vertex. Now, in order to see these, we use the same command, topology.show. So we're going to type topology.show, and we can string them with commas. So E1, E2, E3, E4. And I'm going to use the same option for the vertex size. So I'm going to say the vertex size is equal to 4. And we shift return. or Shift Enter in order to see the result. And here we go. We now have these 4 edges that are forming a square. Okay, so next we're going to actually create a wire, because as you know, these are now 4 independent edges. They're not topologically connected. So we're going to make a wire out of these edges. So how do we create a wire? We can create a wire either by vertices, and it will assume that they are in sequence, so it will connect them all together, or we can do a wire by edges. So I'm going to call this wire W1. So W1 is equal to, the first thing I'm going to try is wire by vertices. So wire dot by vertices, and again, I'm going to give it a list of vertices, so square brackets, and I'm going to say V1, V2, V3, and V4. And I will show this wire. So topology.show W1, and hit Shift Enter. And there we are. Now, how did it know to close this wire? The default is that it closes the wires for you. So there's something called close, and you give it a Boolean, which is either true or false, and it will close it. See, look what happens if I say close equals false. So I'm going to give it an option here. So I'm going to put a comma and say close equals false. And let's run this one more time. And you'll notice now the wire is not closed because you set it not to close it. The other thing you can do to create a wire is to create it by edges. So we can say that W1 is equal to wire dot by edges. And same thing, we do square bracket, and then we give it the edges that we have. And E4. Now with edges, you don't tell it to close it or not. It will just simply take all these edges and make a wire out of them. So topology.show W1. And let's see what that looks like. And again, it's the same wire, but now it is made out of edges. Okay, moving on now to a face. Now this one, as you can see here, is a wire that is made out of edges, but really has no area and has no face that you can calculate anything on. It's just simply a set of 4 edges. So how do we create a face that has kind of like an area and has a front and a back? So one way to do it is simply to say F1 is equal to face by wire, and we give it W1 as the wire, okay? And we'll see what that looks like. So topology.show F1. Here it is. You'll notice, I don't know if it will show on your screen, but this one now has a gray face to it, right? Has a gray color to it because it is a face, no longer a wire. Great. So I'm going to show you now different ways to create faces. So we have some kind of shortcuts. For example, we have a rectangle. So we can say R1 is equal to face dot rectangle, and you can give it a width and a length, and it will create it for you. So I'm going to say the width is equal to 2, and the length is equal to 1. And let's go ahead and show topology.show R1. Oh, sorry, I misspelled rectangle. So R-E-C-T-A-N-G-L-E. Let's try this one more time. And here we are. This is a rectangle 2 by 1. So we can change that, for example, to 4 by 1. And you can get a different rectangle. Another thing is you can create a circle. So we can say C1 is equal to face dot circle, and we give it a radius now. Radius equals, let's say, 2. And let's do topology dot show C1. Here we go. Here's a circle. It is polygonal. It has straight edges. You can increase the number of edges. There's something called sides. You can increase the number of sides. Now is probably a good time for you to look at the API documentation in order to find out what else can you do. topologicpy is a very large software library, and it has a lot of methods. So where do we find them? The easiest way to find the topologicpy documentation is to look to Google topologicpy API space documentation, and it will take you straight to it. It's usually the first hit. You click on the first hit here, and here you have now all the classes that are available in topologicpy. And then when you click on one thing here, one class like face, you get all the methods that are available. As you can see, there's a lot more to a face than just creating it by wire or just creating a rectangle or a circle. But this is how you start exploring. Let's say by edges here, you can find out what the parameters are. And also, even because topologicpy is open source, you can even look at the Python code behind it in order to find out what to do. Great. So let's go back to the next class. So if you remember, the next thing after face is a shell. So let's go ahead and find out how we create shells. Now, if we had two faces that are sharing an edge side by side, we can create a shell out of those two faces. But let me show you some other ways to create a shell. So for example, let's call it S1. We can create a shell as a rectangle from a rectangle, but that has some subdivisions to it. So shell dot rectangle, but in this case, we're going to give it some options. We're going to give it the number of sides on the x-axis and the number of sides on the y-axis. Those are called u sides and v sides. So u sides is equal to 4, and v sides is equal to 3. And let's do topology.show S1. So now we have a simple shell, but is made out of 12 faces, 4 by 3 faces. Now the size of it, the width and the length of it was defaulted to 1. We could have specified that ourselves. So let's go ahead and change that. So we're going to say the width is equal to 4 and the length is equal to 3 in order to match the number of sides, for example. So we have a side of 1. You can do whatever you want, really. Any size would work. And here we have a shell that is made out of these 12 faces. Great. So what is the next class? The next class is a cell. Now, we don't have enough faces that we have created earlier in order to enclose a volume. So we're going to start by looking at the simple way to create cells, which is like, let's say, cubes or cylinders or spheres. Again, if you go back to the API and you go to topologicpy here, and then we go to cell, you'll notice, look at the method that starts by or the method that has a what we call a geometric primitive. A geometric primitive is like a cube or a box or a prism or a sphere or a cylinder or a cone. So we can look for those words. So basically, we have here cylinder, we have a cone, we have probably a prism as well, a pipe, etc., a sphere. So let's exercise some of these things. So let's take a look at a prism. So a prism in topologicpy lingo is basically a box of any dimensions. It's not like a triangular prism that refracts light. No, it is actually a prismatic cuboid. So you'll notice here it has a width and the length and the height, and also the number of sides on the x-axis and the y-axis and the z-axis. They are called UVW, or U sides, V sides, and W sides. But also you can create spheres and cylinders. So let's go ahead and try some of these. So we're going to say that box 1 is equal to cell.prism, and the width is 4, the length is 3, and the height is 2. And let's show that. Topology.show B1. And here we have a prism. By default, topologicpy shows entities, three-dimensional entities, with their faces being half opaque, half translucent, half transparent, or whatever you want to call it. So if you want to see it as a solid with opaque faces, basically you can give the option here for topology.show. It's called face opacity, and it goes from 0 to 1, 0 being fully transparent, 1 being fully opaque. So we can say face opacity equals 1, and run this one more time. Oh, sorry, I misspelled opacity. Happens. And here now we have a fully opaque solid. Let's try a few things. For example, cylinder, we're going to call it C1 is equal to cell dot cylinder, and I'm going to leave it as default, but you can give it options for radius, for height, etc. And then topology.show C1. Here we have a cylinder, and you can change also the number of sides on it. And then moving on to the next API class, which is cell complex. Again, we don't have a lot of cubes or solids in order to create a cell complex, so I'm just going to create a prism, but divided into different sides. So cell complex, I'm going to call it CC1 is equal to cell complex dot prism, and again you can give it U sides equals 4, V sides equals 3, and W sides equals also 3. So basically this is the number of sides it's going to subdivide it or slice it by. So you're going to get multiple cells within this cell complex. And topology.show CC1. And here we go. Now you have a cell complex that has multiple cells. I will deviate a little bit and show you something really interesting. We can take the cell complex and we can explode it out so that you can see the different components of it. So I'm going to call that exploded, and that actually will give us the next class, which is a cluster, and I'll show you why it's a cluster, not a cell complex. So exploded is equal to topology.explode, and you give it CC1. Okay, you can decide on how much you want to explode it by, so how much do you want to separate the cells. And there are also other options, like you can explode the cells, or you can explode the faces or the edges. So we're going to just simply now explode the default, which is the cells of a cell complex. And I'm going to say topology.show exploded. And here we go. So now we have these cells separated. They have a gap between them. If I wanted to increase that gap, I can increase the scale. So I'm going to say scale is equal to 2 and rerun that cell again, the Jupyter Notebook cell. And here we are. You can now see what that looks like. Now, if I examine what this exploded entity is, if I just simply print it here, so I'm going to print, open parenthesis, exploded, you'll notice that it is a cluster object. And the reason it is a cluster object is that these objects are disconnected. They're just simply hovering in space and they're each independent, so it is a cluster. As I said, in this case, it's a cluster made out of only cells. And of course, these cells have faces, and the faces have wires and edges and vertices, but it's really made out of only cells. But you can mix and match. For example, I can say that cluster CL, I'm going to call it CL, let's say. We can say cluster.by topologies, and you can give it now a list of topologies. So for example, square bracket, we can give it, let's look at some of the names that we have. We have CC1, we have B1, and we have S1. So let's go ahead and put those in a cluster. So CC1, S1, and B1, if I remember correctly. And let's print C1, just first of all to see what it is. Make sure we created a cluster. Oh, it's a cell, sorry. CL, not C1, sorry. I'm using similar names. So it should be CL. And it's a cluster. And if I say topology.show CL, and it is everything that we have created before. They happen to be overlapping, but they're really inside the data structure of topologicpy. In the cluster, they are just simply separate objects. That's it from me. I hope you enjoyed this video, and I will see you in the next video.